Multivariate analysis deals with the analysis of parameters during or after the estimation process. It deals with the simultaneous analysis of all elements of the observation vector, and it also deals with the simultaneous assessment of observations and mathematical models. The objective is to determine how well the collection of observations fit the mathematical model after the adjustment was performed, after or during the adjustment. It may be, we may have a filtering process like Kalman filtering, for example, in which we are going to have the parameters being adjusted over time, and these parameters can then be assessed. When we talked about univariate analysis, we had only one probability density function. We used a normal or Gaussian PDF, and that was associated with the set of observations that we were testing. Multivariate analysis deals with a multivariate normal or Gaussian PDF, in the sense that we have all the observations that have gone through the process, and they are all now part of the same package. So when we have our result, we basically have not just one PDF, but we have several PDFs, and that could be, we could see that basically as a surface. So what we have in this equation is essentially we have the normal distribution, the Gaussian distribution normal, and here we have the event or the parameter that we are testing, and you should pay attention that it is underlined, so which means that they're dealing with a vector. We have the population mean, and again this is several values, and we have a covariance. So the population, instead of having just one mean and one variance, now we have a vector of means, each mean corresponding to, say, a parameter or a residual, and we have a covariance matrix. And how this normal distribution is built, it is Gaussian, of course, so this term here represents the Gaussian distribution. And what we have here basically is a ratio. We have 2 pi multiplied by n over 2, and n in this case represents the number of observables. The number of observables that were fed into the mathematical model. The determinant of the covariance matrix, and here we basically have a quadratic form. If you look at these, it is a weighted quadratic form in which what we have is the parameter minus the mean. So this would be parameter mean, population mean. These tests, they will be grouped again in tables. We're going to go over the tables briefly in a few moments. We have table 13.4, table 13.5 in the reference textbook, just as the concepts. Table 13.4, it talks about the so-called chi-squared goodness of fit of residuals and misclosures. So this is basically, we're looking at how residuals and misclosures organized in histogram, how they match a postulated probability density function. Test of the quadratic form of the residuals. And this test, essentially, we're going to look into the compatibility between the a-priori variance factor and the a-posteriori variance factor, and a test of the quadratic form of misclosures. Table 13.5 talks about assessment of residuals and misclosure outliers, and assessment of estimated parameters. So essentially, what we have in here, we have the input observations, okay, so given in this black ellipse. The observations will feed the adjustment, which means it goes through the mathematical model. So our parameters and their covariance matrices, they are a result of both the input observations and the mathematical model. So we can have the assessment of estimated parameters, and here we are, estimated parameters as x hat and it's their covariance matrix, cx hat, assessment of residuals and misclosure outliers. So here we have residuals and misclosures. We can still check if there is any outlier. Outliers here would be a consequence of either outliers that were not detected in the univariate testing, the test before the adjustment, or anything that was somehow a byproduct of the mathematical model. Test for the quadratic form of the misclosures, again dealing with misclosures, want to see if misclosures are normal. Test of the quadratic form of the residuals, so a test that is going to involve the a-posteriori variance factor. Goodness of fit of residuals and misclosure, and here we have the we look at the normality of the histogram formed by residuals and misclosures. In general, univariate tests are performed before the adjustment, and multivariate tests are performed after the adjustment. Well, as I say, we may have a stepwise adjustment that in this case we may have these parameters as the adjustment is being performed. Univariate tests are concerned with the quality of the data. Multivariate tests are concerned with the quality of the parameters and the mathematical model. Here we have the tables, table 13.4. We have here the goodness of fit of residuals and misclosures. It follows the same process of the test of histograms that we did before the adjustment. Okay, the situations that we have as far as the population parameters is concerned is that we know the mean value, because the mean value of residuals and misclosures is expected to be equals to 0. So this is the population mean. And now we have something that is a different paradigm, is that we are going to look at the a priori variance factor. Do we know the a priori variance factor? Do we not know the a priori variance factor? If we know the a priori variance factor, we use the covariance matrix of the estimated residuals and the covariance matrix of the misclosures. If we don't know the a priori variance factor, we are going to use the posteriori variance factor to scale the covariance matrix of the residuals. Okay, so we have now, we usually have the covariance matrix of the estimated residuals, for example. If we don't know the posteriori variance factor, we scale it with the a posteriori variance factor, and now we're going to have this matrix C hat, R hat. The null hypothesis, it's normal distribution. The statistic is the same. The PDF for the test is the same, and the test itself is the same. So the mechanics is the same. Now we have the test for the quadratic form of the misclosures. We're basically are going to see if the quadratic form of the misclosures, okay, lies between, this is going to be our statistic. We're going to test if that is between a certain interval. Okay, if it is, we can say that the misclosures have a normal distribution. Again, we have these two situations. We either know or we don't know the a priori variance factor. And the test of the quadratic form of the residuals, this is a very intriguing test that we perform, and we're going to discuss really the meaning of this test and what to do if this test fails. Okay, we are testing again the a priori, the statistical compatibility between the a priori and the a posteriori variance factor. This is the statistic. Why? But we are reformulating it in such a way that we test whether the a priori variance factor lies within an interval that is a function of the degrees of freedom, function of the a posteriori variance factor, and a function of the value that we draw from the chi-square distribution. And again, we are the test, the null hypothesis is that the residuals have a normal PDF. The other table deals with the tests on outliers. Okay, so we have residuals and we have misclosures. So residuals, we know that their mean, we expected mean equals to 0. The same for the misclosures, so which means we can consider that we know the population. And likewise, we have now faced with the decision whether we know or we don't know the a priori variance factor. And the decision, if we don't know the a priori variance factor, we have to rescale the covariance matrix of the parameters. So this is the statistic R, but what we will be doing, essentially, we'll be testing if the estimated residual, okay, each estimated residual lies within an interval. This is a two-tailed test, okay, and from one side we have the value that we draw from the normal distribution. Here we have the standard deviation that we get from the covariance matrix of the residuals. This is negative from one side, minus psi sigma in here, and here we have plus psi sigma. If we don't know the a priori variance factor, we are going to scale the covariance matrix. Okay. One thing that we're going to discuss is that the residuals used in the test, they, as a matter of fact, they are standardized, and we're going to see why they have to be standardized. The test for misclosure outlier, which is not as popular, but as used as the test of residual outliers, but it's always important, particularly if we deal with the conditional case of adjustment. We have a similar situation in which the misclosures are standardized, and it's also a two-tailed test. The estimated residuals, they have some properties that are very useful, okay? And we can use these properties to see if there is anything wrong. For example, the estimated residuals should show no systematic effect. It is somehow obvious, because if we treat the observations for systematic effects before the adjustment, if we take away blunders and everything, so we should only expect to have random errors, okay, random variation in the residuals. The constituents of the residual vector, they are correlated, okay, independent on whether the original observations were correlated or not. Okay, so and why is that? Because during the adjustment we create a mathematical correlation. So the observations, they get correlated, and therefore during the adjustment, the residuals, the estimated residuals, they will have a fully populated covariance matrix of the residuals. Okay, if you recall, what quantity tells us about the statistical dependence or not? Well, covariance matrix. The covariance matrix will have the variances, right? And then we have the covariances in here. And if it's fully populated, we have the statistical dependence. If the covariance matrix is just variances and we have 0 of diagonal elements, this is a 0 here, it means that there is no statistical dependence. The residuals will always be that, okay? Always be that. When you talk about the estimated residuals, we refer to observations and mathematical models. Again, this is important. The behavior of the residual indicates the behavior of observations and mathematical model. Testing of adjusted observations and model is normally done through residuals. So residuals are a very important quantity. They are not just something that we ignore. Okay. If you're going to if you're shopping for an estimation package, adjustment package, and it doesn't provide residuals, get rid of it. Okay, it may be good, but it's missing one thing that is very, very important. We learn a lot from the residuals. That's why these tests on the estimated parameters after the multivariate tests, they use residuals quite a lot. So keep in mind, property of estimated residuals. Okay, they should be only random. They are correlated. Okay, they indicate behavior of observations and mathematical models, which means if something funny happens with the residuals, if you look at the plots of the residuals and there is a systematic effect, it is either something that was not properly treated in the observations, or it is a byproduct of the mathematical model. Misclosures. Now the misclosures, here we can talk about two types of misclosures usually. Here we are talking the W prime comes from the conditional model. Okay, so for example, and the conditional model is very good if you have closed loops like a leveling or a gravity network. So we have these loops, and what happens is that we can, for example, compute the misclosure within these loops. An example, the triangular the triangle angular misclosures. For example, the ones that we used when we dealt with the example on the univariate test on the histogram, the chi-square goodness of fit test. Okay, so which means that these misclosures here, they do not depend on the initial values of the parameters. So we are not referring to the misclosure that results from the linearization, this type here. Okay. Both misclosures and the residuals have similar statistical properties. So they both have zero mean, their covariance matrix is fully populated, the probability density function is assumed normal, and they are tested in the same way. Now let us talk about the standardization, or also known as the homogenization of the residuals. This needs to be done because each residual will represent one of the observation sets that were collected before the adjustment. And each one has its, because each one of these observation sets, they belong to different populations. So, which means they have different normal distributions, they have different means and different standard deviations. The PDF of each individual residual will be different. So that's why you have to standardize. So when we standardize the residuals, we make all of them having the same mean 0 and standard deviation +1 -1. Okay, so which means they are homogeneous. How these standardize, which means that now we have one PDF for the standardized residual R tilde, okay, which is all the same. How this standardization takes place, it takes place by dividing each one of the residuals by its corresponding standard deviation that comes from the covariance matrix of the estimated residuals. So, which means that by doing that, we have now a set that is standardized. The same procedure can be done for the misclosures. But remember, in these multivariate tests, we have all these two situations. We either know the a priori variance factor or we don't know the a priori variance factor. If we don't know, we are going to use the a posteriori variance factor. So, if the a priori variance factor is not known, we will consider that our matrix CR hat, matrix, the covariance matrix of the estimated residuals, is not properly scaled. So we need to scale it, and we do the scaling again using the a posteriori variance factor. This is hat, this is okay. Now the standardization is going to be done by the ratio of each individual residual by its scaled covariance matrix of the residuals. Okay? So which means it's still the same procedure. The difference now is that the standard deviation comes from the scaled covariance matrix of the residuals.